And folks in the chat hear me okay? Okay, folks, so as always, don't forget the seating survey. I have been working on trying to figure out the best way to do curves on the exams because of the where the grades were on the second exam. I have decided to go ahead and curve both the first and the second exam grades. I believe about 15 minutes before class, I finally figured out the best way to do that. So I will be posting about the details of that shortly this afternoon. I'm not planning right now to go into detail on the exam questions in class because I want to put together an exam walkthrough so that you'll have that to go through. And in addition, because I am doing because the content videos this week are not up, I am spending the first 2 days of class, yesterday and today, separately going through the content for this week's Newton homeworks. So I'm going to be lecturing on that material today. It's the same material that I went over yesterday. So if you happened to watch that video or attend yesterday, there's not going to be anything new today. It looks like I will be able to, I'm able to cover all of that material in one class period. So the goal would be for tomorrow and Thursday's classes to be answering questions and such. So do we have any logistical questions before I get started on that content? Okay. So let me switch this here. Okay, so our topic for this week is acids and bases. And one of the issues we have with acids and bases is that there are multiple definitions of acids and bases that we have to worry about. The first definition is the Arrhenius definitions. The Arrhenius definitions say that an acid is a substance that when placed in water dissociates to give H plus ions, and that a base is the same thing, but giving OH minus ions. So one of the advantages of this particular set of definitions is that it is substance-based, meaning that a substance is either an acid or it's not. It is either a base or it is not. So it's relatively clear-cut in that regard. There are, however, okay, so let's look at a couple of examples of this. So for an example of an acid, we could have HCl, aqueous, which when placed in water forms H plus aqueous ions and Cl minus aqueous ions. And so this would be an Arrhenius acid. Similarly, sodium chloride, when placed into water, that's not sodium chloride, excuse me, sodium hydroxide, when placed into water, will dissociate to form sodium plus ions and hydroxide ions. And so this would be an Arrhenius base. The key criteria are these two ions. This is what makes something an acid. This is what makes something a base. Now, the Arrhenius definitions do have some disadvantages, unfortunately. One of them is that it's limited to talking about water. Substances in water. And there are plenty of cases where we have acid-like or base-like behavior in solvents other than water. And so the Arrhenius definition is somewhat limited in that regard. Probably more importantly, there are certain substances that when placed in water do in fact form, say, the hydroxide ion, but they don't do it by dissociation. So an example of that would be ammonia, which when placed in water has an equilibrium forming NH4 plus ions and OH minus ions. So what's happening here is that the ammonia is pulling an H plus from the water molecule and leaving behind an OH minus, a hydroxide ion. So this substance, ammonia, kind of acts like a base because you end up with the hydroxide in aqueous solution, but it is not happening through a dissociation process. So we would like to be able to call this a base, but the Arrhenius definition doesn't let us do that. Because of these limitations, while the Arrhenius definition was sort of the first modern definition of acids and bases, it has kind of fallen by the wayside and is no longer really used very much. The second definition, and the one that we are going to be focusing on primarily in this class, is the Bronsted-Lowry definition. Which says, this was proposed by two scientists independently at the same time. And this one says that an acid is a proton donor. And it says that a base is a proton acceptor. Now, when we're talking about donating a proton or accepting a proton here, we are not talking about a nuclear reaction where we are doing something changing the number of protons in a nucleus. What we are talking about as a proton is the H plus ion, because what we have in the H plus ion is a single proton that is lacking its electron. So that's what we mean in this case. So let's take a look at the example we looked at before here, the hydrochloric acid, and see what exactly is going on in the Bronsted-Lowry definition. So what is happening is that we have HCl, aqueous, and it is interacting with water to form the Cl minus aqueous ion and the hydronium ion aqueous. Now, let's think about this for a moment. Why did I draw it differently than I did up here? The reason is that in an aqueous environment, H plus by itself doesn't really exist. An isolated proton, which is what the H plus ion is the most concentrated bit of positive charge you can imagine because there's no electron around it. And so the H plus ion in water is going to associate itself with a lone pair on a water molecule. Remember our Lewis structure of water, we have two lone pairs of electrons floating around, around the central oxygen. And so our plus charge on the proton is going to associate with one of these lone pairs to make, I'm doing this wrong, here we go. This ion right here. So this little sort of square bracket I have on the side with a plus sign means that there's a plus charge on the ion as a whole here. This is not a 7 plus. This is a sort of just an indication that we have a, this plus is somewhere on the whole molecule. So in an aqueous environment, we do not actually have H+ ions. We have these hydronium ions that are formed. Even that, however, is a bit of an approximation because this molecule will then associate with other waters. So we'll have, it could be H3O plus, it could be H5O2 plus, it could be H7O3 plus, and so on, depending on how many of them are kind of tied together in this complex that is formed. So when we write H+ aqueous, we need to remember that this is really just a shorthand notation that we use to describe H3O plus, H5O2 plus, H7O3 plus, that sort of combination of possibilities. H3O plus is a similar shorthand, but it is at least acknowledging what is going on with the proton to some degree. And so in many ways, the H3O plus is a better representation of what's actually going on. So with that in mind, take a look now at what is happening in this reaction. We have the HCl, which is donating a proton to the water. So this HCl is a proton donor, and so it is a Bronsted-Lowry acid. The water, in this case, is accepting the proton, and so it is a Bronsted-Lowry base. The thing to notice here, in contrast to the Arrhenius definition, is that this is not a substance-based definition of what an acid or a base is. This is a reaction-based definition of what an acid or a base is. Something acts as an acid in a reaction, or it acts as an acid as a base in a reaction. And that's important to notice because if we look back up here at this formula we looked at a moment ago, where we said the Arrhenius definition didn't allow us to call this a base, we have the water donating a proton to the ammonia, and so the water is acting as a Bronsted-Lowry acid, and the ammonia is acting as a Bronsted-Lowry base. And so we are able, within the Bronsted-Lowry definitions, to account for this kind of behavior, whereas in the Arrhenius definition we couldn't. But also now notice that in this reaction, water is acting as an acid, whereas in this reaction, the HCl reaction, water is acting as a base. So the nature of a substance, whether it is an acid or a base, depends upon which reaction you are talking about at the time. Water here, it can, as shown by these two reactions, can act as either an acid or a base, and we have a name for that, amphoteric. Amphoteric means it can act as an acid or a base depending upon the reaction. Okay, so this is the Bronsted-Lowry definition, and it is the primary definition we are going to be using in this class. There is, however, a third definition that we need to be aware of, particularly because it plays a very strong role in understanding organic chemistry, which you'll see in a future class. This is the Lewis definitions, and this is the same Lewis that is the namesake of the Lewis dot structures. This one says that an acid is an electron pair acceptor, and a base is an electron pair donor. Okay, so to understand how this definition works and how it relates to the other definitions we were looking at, we need to look at the Lewis structures over the course of the reaction. So what I'm going to draw here is our HCl dissociating in water reaction. And I'm going to introduce to you an organic chemistry type of notation here, which is known as arrow pushing. The way arrow pushing works is that an arrow that you draw describes the movement of electrons. And so what we would draw this reaction like this to give us that and that. So the lone pair on this water is moving over to attach to the hydrogen atom, and that is in turn pushing the electrons away from the hydrogen atom that were initially in the chlorine-hydrogen bond back over onto the chlorine. And so what we can see here is that the water is acting as an electron pair donor in this reaction, and the HCl is acting as an electron pair acceptor. So in this reaction, this is called a Lewis acid, and this is called a Lewis base. So in all three cases, we determine that in all three types of definitions, we determine that HCl is an acid and is acting as an acid in this particular reaction. So there's consistency among them. But as we go from Arrhenius to Bronsted-Lowry to Lewis, we get towards more and more general types of behavior. So for example, in the Bronsted-Lowry definition, we can have an acid-base reaction that has nothing to do with water and has nothing to do with hydroxide or hydronium ions. So we could have, for example, a CH3O minus ion reacting with an ammonium ion to give us CH3OH plus NH3. And so what we have here is a proton donor, a proton acceptor. We have a Bronsted-Lowry acid-base reaction happening, but this has nothing to do with hydronium ions, has nothing to do with hydroxide ions, has nothing to do with water. Similarly, we could have a reaction. I'll use the same CH3O minus ion here, reacting with formaldehyde to give us something like this. And we have a Lewis acid-base reaction happening, an electron pair donor, electron pair acceptor, and there's not even a proton transfer going on. So we have this sort of hierarchy of these different definitions where the Arrhenius definition is the most restrictive because it's all talking about water. The Bronsted-Lowry definition that generalizes that somewhat to talk about proton transfer processes. And then the Lewis acid-base definitions, which generalize that even further to talk about electron pair donation and accepting, where a covalent bond ends up getting formed as a result of that process. So, as I mentioned, we are going to primarily in this class focus on the Bronsted-Lowry definition, but keeping in mind the Lewis acid-base definition for future studies, for once you get into organic chemistry, is a very useful thing to do. Okay. Any questions on the definitions before we start getting into some deeper topics with them? Okay. All right. Let us talk now about about water, because acid-base behavior in water is some of the most important chemistry we have, because it dominates a lot of biochemistry, it dominates a lot of environmental chemistry. So a key reaction to understand from an acid-base perspective is what is known as the autodissociation of water. This reaction here is an equilibrium that is always happening very rapidly within a sample of water. We have water molecules where a proton is getting donated from one of the water molecules to another of the water molecules, forming both the hydronium ion and the hydroxide ion. And so in this reaction, in a Bronsted-Lowry sense, water is behaving as both the acid and the base in this reaction. Now, because this reaction is always happening, and we have an equilibrium going on here, we have, when we're thinking about how much hydronium or how much hydroxide we have, it has to be in the context of this reaction happening. This reaction at room temperature has an equilibrium constant, which, because it is so important, has a special name, Kw, where W stands for water, which has a value at room temperature of 10 to the negative 14 molar squared. Now, I very, very seldom tell people that there's a detail you should memorize. This particular detail is so central to understanding acid-base behavior that this is one of those numbers you should probably remember. So let's think about what this equilibrium constant means. If we write our equilibrium constant expression, it is simply the concentration of the hydronium ion times the concentration of the hydroxide ion. And if we imagine starting this reaction with, think about an ice table. If you imagine starting this reaction without any hydronium or hydroxide, then because of the reaction stoichiometry, you are going to get equal amounts of hydronium and hydroxide, which means that in neutral water, our hydronium ion concentration and our hydroxide ion concentration will be equal, and they will be equal to 10 to the minus 7th molar. Because 10 to the minus 7th molar times 10 to the minus 7th molar is 10 to the minus 14th molar squared. Now, Le Chatelier's principle applies to this reaction just as it does any equilibrium. So if you imagine taking, say, hydrochloric acid and adding it to water, and as a result, this reaction forms hydronium ion. That hydronium ion that gets formed is a perturbation on this equilibrium. And so which direction is this equilibrium going to shift? Yep, that's right, towards the left, towards the reactants. And so with that happening, the hydroxide ion concentration is going to go down as a result. So let's suppose that we have our ice table. So let's suppose that we dissolve enough hydroxide, we dissolve enough hydrochloric acid in solution to make the hydronium ion concentration up to, say, 0.01 molar. Okay. Actually, we don't even need to draw this out as an ice table. Let's just look at it as we make our hydronium ion concentration 0.01 molar. We can then simply take our Kw here to determine the hydroxide ion concentration. And we find that this here can be written as 10 to the minus 2 molar. And so in order to have this times this equal 10 to the minus 14, this is going to have to be 10 to the minus 12 molar. Okay. So what we have here is an illustration of how Le Chatelier's principle will cause the reaction to shift back to the left. And just from the equilibrium constant for Kw here, we can determine what our hydroxide ion concentration is. Now, when we are talking about concentrations of hydronium and hydroxide, it is extremely common to have many orders of magnitude difference between the two. As a result of that, chemists tend to use what is known as a P scale. P anything is equal to negative log base 10 of that thing. So pH would be negative log base 10 of the hydronium ion concentration. pOH would be negative log base 10 of the hydroxide ion concentration. So in this case, if our H3O plus ion concentration is 10 to the minus 2, then that means our pH of this solution is going to be 2. So 10 to the minus 2, we take the exponent by taking the log base 10, and then change its sign, it becomes 2. And our pOH of this same solution is going to be 12. Okay. And what you should notice here is that pH plus pOH will always equal 14 because the product of these two concentrations is always going to be 10 to the minus 14. Okay. So pH plus pOH equals 14. Okay, and notice as well that neutral water has a pH and a pOH of 7. So what this means is that if we have a pH lower than 7, then we have more hydronium than we do hydroxide, and so it is an acidic solution. If we have a pH higher than 7, we have more hydroxide than we do hydronium, and so the solution is basic. Okay, any questions on the pH scale and on the autodissociation of water? No? Okay. All right, let's talk about these reactions in terms of an equilibrium. So let's imagine that we have our HCl plus H2O yields H3O plus plus Cl minus. And we're going to compare that to CH3COOH. This is acetic acid, which is the acid that is in vinegar, plus H2O is in equilibrium with H3O plus CH3COO minus. Okay. Now you notice I wrote the first one as a reaction that is going only from left to right, but I wrote the second one as an equilibrium. And that is because in the first case, in the first reaction case, every bit of HCl that gets into water does in fact dissociate. You can think of that as this reaction having such a ridiculously high equilibrium constant that the reverse reaction is essentially negligible. Okay. But in the bottom case, there is some undissociated acetic acid in equilibrium with the acetate ion. So you're always going to have some of both of those. This distinction between it always dissociates completely versus it is in equilibrium is our distinction between a strong acid and a weak acid. Now, it is important to avoid a pitfall in thinking about these. A lot of people look at, oh, strong acid, that means that it's going to have a very low pH. No. A strong acid simply means that however much HCl you have in there, all of it dissociates. But you could have a very dilute solution of HCl, and so its pH is going to be really close to 7, just slightly below it. Whereas you could have a very concentrated solution of acetic acid, and so it would have a very, very low pH and lots of hydronium ion, but it is still a weak acid because it is in equilibrium with, the acid is in equilibrium with its, with the deprotonated version of it. Yes? Will strong acids always be in a reaction going one way? In their reaction with water, yes. It is possible for them to enter into a reaction with something other than water where it would be in equilibrium. Okay, so let's take a look at doing an example ice table for this acetic acid reaction. So I'm going to abbreviate acetic acid as simply HA, where A here is meaning the acetate ion. So we have HA plus H2O is in equilibrium with H3O plus plus A minus. Okay. So the equilibrium constant for a weak acid reaction has a special designation, Ka, meaning equilibrium constant for the acid reaction. Ka for acetic acid. So this particular acid has a Ka of 1.8 times 10 to the minus 5 molar. And if you look at the structure of the reaction, this is H3O plus times A minus over HA. Okay. Now let's suppose that we make our solution of acetic acid, our vinegar solution, where we have 0.01 molar acetic acid, and we want to know what our pH is going to be at the end of it. So we set up our ice table. I'm going to mark this as something to come back to. I will explain what's going on in a moment. We have to go, this has to be the negative side because the reaction has to shift to the right since these are zeros. X, X, 0.01 minus X, X, X. And so we have now our Ka of 1.8 times 10 to the minus 5 molar equals X squared over 0.01 minus X. We can multiply this through and have 1.8 times 10 to the minus 7 molar minus 1.8 times 10 to the minus 5 molar times X equals X squared. We can put this into our into the standard quadratic quadratic arrangement. 1.8 times 10 to the minus 5 molar times X minus 1.8 times 10 to the minus 7 molar equals 0. And what I would do at this point is then look up or go find a quadratic formula calculator. We would put in as A, 1, as B, 1.8 times 10 to the negative 5, and our C is negative 1.8 times 10 to the negative 7. Calculate the answer. Only one of the two roots is positive, and we get 0.00042 molar. And so, since this is our X right here, our pH would be the negative log base 10 of that. And so I'm going to plug that into our into a calculator. I'm using Wolfram Alpha right now because I don't have a scientific calculator with me. So that gives it a pH of 3.4. Okay. Now, something to notice in doing this is that I set our initial concentration of hydronium ion to be 0. But we said that water initially starts out neutral at 10 to the minus 7 molar hydronium ion. So I was able to leave this as 0 in this case as long as I check afterwards to make sure that the result, X here, is large compared to our 10 to the minus 7 that should have been in this box. Okay, so in this case, 4.2 times 10 to the minus 4 is quite large compared to the 10 to minus 7 we started with, so it is perfectly fine to neglect the initial concentration of the hydronium ion here. Okay. Any questions on how this kind of ice table works for acid-base reactions? Okay. How do you solve that equation with a calculator? Yes, the quadratic formula. So negative b times plus or minus the square root of b squared minus 4ac all over 2a. Let's see. So just like the concentration of the hydronium ion and the concentration of the hydroxide ion, which we decided to use the p scales for in order to be able to deal with decimal numbers rather than having to go into scientific notation. You can similarly represent equilibrium constants using the p scale as well. And so this would have a pKa of negative log base 10 of 1.8 times 10 to the minus 5, which I will put in here, 1.8 times 10 to the minus 5, and we get a pKa of 4.882, something like that. So remember, so it's important to understand the p-scale in general because all sorts of things can be represented on the p-scale. And so going from a concentration or a Ka or something to the p version, you do the negative log base 10. The inverse of this process is that our item equals 10 to the minus p item. So our H plus concentration is going to equal 10 to the minus pH, or our Ka is going to equal 10 to the minus pKa. Okay. Any questions on the p-scale stuff? No. All right, let's see here. Something in the chat. Okay. Let's look at this reaction a little more closely now. Notice that because the reaction is reversible, the reverse reaction is also a Bronsted-Lowry acid-base reaction. So let's take a look now at this example. HA plus H2O in equilibrium with H3O plus A minus. Now, because in the forward reaction, the HA is what is donating a proton. This is our acid, and the water is our base. In the reverse reaction, the H3O plus is donating the proton. So for the reverse reaction, the H3O plus is our acid, and the A minus is our base. And because there's a relationship between the left-hand side and the right-hand side, there are special names for these. This is the conjugate acid and the conjugate base. So if you have an arbitrary acid HA, its conjugate base is A minus. Now, let's take a look at that reverse reaction. If we write this the other way around, A minus plus H3O plus in equilibrium with HA plus H2O. Now, we can easily add to this reaction the equilibrium that is already going on with water. 2H2O is in equilibrium with H3O plus OH minus. We add these together. A minus plus H3O plus 2H2O is in equilibrium with HA plus H2O plus H3O plus OH minus. We cancel out what we can, and we get A minus plus, H2O is in equilibrium with HA plus OH minus. This reaction is the reaction we would write down if we wanted to write what is the standard base reaction. And so the equilibrium constant for this reaction, we give the notation Kb for the equilibrium of the base. So that's going to be HA times OH minus over A minus. And because these reactions are related to each other, the acid reaction and the base reaction for the conjugate base, there is a relationship between the Ka for the acid and the Kb for its conjugate base. That relationship is Ka times Kb equals Kw. So if you are ever in a situation where you need to deal with the base reaction, then you can find the equilibrium constant from its conjugate acid, acid's Ka. Okay. I'm not going to do it here, but when I do have the content video for this up, for anyone that is interested, I will go through the derivation of this particular step, but I'm not going to be testing you on the derivation of it. It's just going to be there as further information so that those of you that are interested can see where it comes from. Okay, so any questions on the relationship between Ka and Kb and about conjugate acids and bases? Okay. Okay, I think that is pretty much all of the content that you need to know for the Newton homework this particular week. Has anybody that has started the homework come across any questions that are not addressed by what I've just gone over? No? Okay. All right, well, that is all the new information I was planning on going over today. So I will happily open this up to any questions anybody has about absolutely anything. So since we have some time left. Anybody have anything you'd like me to talk about? All right then. Well, I guess we're going to have a short class period today. So I will be posting this afternoon to Piazza about how the curving of the grades is going to be working. I am hopeful as well that I will be able to get the exam walkthrough video up very soon. And I know I am somewhat behind on answering Piazza questions right now. I will get onto that as well. And thank you very much.